Okay, so welcome to the video that starts concluding the material from the 21st lecture. We're going to focus on electrocardiogram and electroencephalography. And electroencephalography is really a very short and very small portion of this lecture, so it's just going to be covered by principles. We're going to cover the shape and idea and the mechanism of the myocardium action potential, just to the very essentials. And if you don't really want to review this, because I haven't really seen this in an exam represented, I've seen electrocardiogram, but I haven't seen the myocardium action potential. So if you want to skip it, it is okay. It's not a necessity. And then we're going to review the measuring, how to measure a current from action potentials in a biphasic manner. And this is really important. You don't want to skip this one. You don't want to skip this one. This one you can't skip, this one don't. So we're just going to keep on going, and this is the idea of how a myocardium action potential looks like. And this is just from the lecture slide, so you should be able to understand what the lecture slide is talking about. And this is the membrane potential on the y-axis and time on the x-axis. I haven't placed any values here because it's not really important to understanding what's going on. So we already know from action potential we have our resting membrane potential, influx of sodium, depolarization, sodium channels get inactivated, efflux of potassium, and then repolarization, hyperpolarization, and we gain our resting membrane potential again. Now the question is, how is this? We already said this shape is different for each cell type. So how does the myocardium cell type looks like for its action potential? So let's see. First of all, we have our resting membrane potential, at which point we already know that we have influx of sodium. Sodium channels open at this point. So sodium channels will open and sodium would flow into the cell. Sodium would flow into the cell. And what would happen at this point? We know that at the point of influx of sodium, we were going to have depolarization. Very good. And at this point, we already know that there's inactivation for the sodium channels, and sodium is going to stop flowing. And we already know that at this point, the delayed opening of potassium is going to cause potassium to come out of the cell. And that's going to start showing us some repolarization. But the interesting thing is that shortly hereafter, having the potassium channels open and potassium flowing out, we have calcium channels opening as well. And if we try and understand how much is calcium concentrated compared to the inside and outside of the cell, well, we know if this is the inside of the cell and we're looking at calcium, we have a little bit of calcium inside of the cell, and we have a lot outside of the cell. We have a lot compared outside of the cell. We're talking about 10 to the negative 4 micromolars to right around maybe 1, 2, 3, or 4 micromolars outside. So what we're looking at really is that calcium is going to go inside the cell. Calcium is going to go inside of the cell. And this is only for a short while, but you can imagine that calcium going out is us gaining positive charge, and calcium going in is us gaining positive charges, and potassium going out is us losing positive charges. For this short period of time, we're going to lose positive charges, but we're going to gain positive charges. So the resting membrane potential, or rather the membrane potential itself, is not really going to change drastically. It's just going to go down to a very small extent. Potassium is not going to have such a great impact on our repolarization. And this is called the plateau. And at this point, right around this point, we can assume that these calcium channels close. And therefore, just going to close them at this point. Calcium channels close, and potassium channels are still open. And potassium is still escaping. So now potassium is going to actually prevail, and we'll be able to get us our membrane potential back to our resting membrane potential. And now we're going to get the repolarization phase in a nice repolarization in a nice downward angle. So this is why the myocardium action potential looks like this. This is the idea behind the shape of the myocardium action potential. And now we can keep on going. We're going to keep on going, and now we're going to review how to measure a current from action potentials. And if you've just joined us, welcome. And this is really very important to understanding how an EKG works, how an electrocardiogram works. And basically what I'm asking is, and let's just say that we have the giant axon squid that we were actually researching in voltage clamp. We inserted an electrode here, and we had an electrode in the outside solution, and this is how we can actually measure the membrane potential here. But we can't really, if we want to measure how an action potential of the heart works, we can't really insert an electrode to our patient's heart. It's probably not going to be very advantageous and maybe cause more damage than we're trying to remedy. And this is called a monophasic measurement, because it only features one electrode that is coming in contact with that given muscle. But really, we can't do this. This is not very applicable if we're talking about measuring the action potential of any other giving cell. So basically, what we can do is, let's just say this is the cell surface, and this is going to say, all right, let's make it a little bit bigger, make it a little bit more comfortable, a little bit bigger here. Let's just say that this is the intracellular, and these two sides are the extracellular. And what I can really do is, instead of having something poke into the inside of the cell, I can just put electrodes. I can just put electrodes on the outside of the cell. Put electrodes on the outside of the cell. Let's say here and here. Put electrodes on the outside of the cell and attach them to some sort of, well, we can say some sort of galvanometer that would measure current for us. And in this way, if I have some sort of currents moving through, I would be able to measure the potential difference between these two sides. So really, I would only get a reading if one side is more positive than the other. Then I'm going to get a reading. But if I'm looking at the beginning, let's just say this is the beginning, the whole muscle tissue is polarized, it's all negative, then I'm obviously not going to get a reading. I'm not going to get a reading here. So let's try, and I'm just going to draw a galvanometer here. This is my galvanometer. I'm just going to point the needle in this direction now, and we're not going to measure anything. This is our measurement. We're not going to measure anything. And you can imagine that these two are placed in specific manner, in which if I measure this side more positive than this side, my galvanometer is going to go up. And if I measure this side more positive than this side, my galvanometer is going to measure a downward angle. This is just some sort of standard, some sort of industry standard, and we're going to get to that. Don't worry about it. So what would happen now? Let's just say there's some sort of depolarizing wave coming this way, and it's going to turn all of this side. It's going to turn all this side positive. This side is suddenly going positive. Well, you can imagine that this wave is going to propagate in that direction. So what do we measure now? What do we measure now? Well, basically, being that the left side is more positive than the right side, we can imagine, what the hell is this? We don't need that. We can imagine that our galvanometer is going to measure a current this way. So we're going to have some sort of an upstroke here, as we have this depolarization wave propagating that way. So, and this wave is eventually going to get to this side. So let's move it. We're going to take it and move it. We're going to take it and move it to the right side here. It's slowly moving, and it's being chased. It's being chased by our repolarization waves. And you can imagine that this tissue now is being repolarized through different mechanisms that we already learned. And this wave here is just moving in that direction. So now, as you can may well imagine, being that we don't have any difference between this measurement here and this measurement here, then our galvanometer is just going to show us a straight line, because it's not measuring any difference, because this wave is in between these two electrodes. So we're just going to go back. We're just going to go back to measuring nothing. So this is just going to go here when their measurement is like so. Very good. So this is our measurement. So what's going to happen next? We already know this is just the same old song. What's going to happen next? We can expect this wave to just propagate to the right side and reach this electrode on the right side. And we already stated that when this side is more positive than this side, we're going to get a positive reading. on our galvanometer. And when this side is more positive than this side, we're going to get a negative reading on our galvanometer. So our galvanometer is now, let's fix the reading here in our galvanometer. Our galvanometer, and if you have no idea what a galvanometer is, it is not super necessary to understanding electrocardiogram, so don't worry about it. So our galvanometer is going to give us a slightly negative reading here, and we're just going to go down like so. Very good. And at this point, you can already imagine what is going to happen. This wave, this propagating, I wouldn't say wave, but this propagating action potential is going to just leave this area of inquiry. It's just going to leave our area of interest. And this whole tissue is going to get repolarized again. And being that if you look at the difference between the right side and the left side, you might already notice that there is no difference. There's no difference between this measurement and this measurement now. So what is our galvanometer going to show us? It's going to show us a no net charge or no net flow, and we're just going to find ourselves in this initial state. And this is basically how we can use two electrodes. What am I doing over here? This is just how we can use these two electrodes to measure the propagation of action potential without inserting any invasive electrodes in. And this is called a biphasic reading. You don't really need to remember that. If you already know electrocardiogram because you've learned it and you forget that it's biphasic, it's probably not super important for your biophysics exam. Perfect. So this is how you measure currents from action potentials. And we're really going to use this to understand this whole thing that is going on electrocardiogram. It's probably not going to look like this, but this is just an oversimplification. We're going to have upstrokes and downstrokes, and we're going to be able to explain those via the direction of propagation of your action potential. Perfect. So see you in the next video.